Welcome, ladies and gentlemen. Let's go ahead and share how the two terms series and sequences are related. So how are series and sequences related? Kobe?
Series is the sum of a sequence.
Absolutely. So a series is the sum of the terms in a sequence. Thank you. The sum of the first n terms in an arithmetic sequence with first term a sub 1 and constant difference d is given by, and I don't know that we need all of those, but we do know an arithmetic sequence, right, has terms that are separated by that constant difference d. What is my partial sum s of n given by for a sum of n terms from an arithmetic sequence? Sophia?
N times a1 plus a of n.
Thank you. And so it's n times the sum of a sub 1 plus a sub n. That's the first term and the last term in the sequence that I'm summing. And then all over 2. Raise your hand if you have the same thing as Sophia. Have that? Great. And then lastly, the sum of the first n terms in a geometric sequence with first term g sub 1 and constant ratio r, that multiplier between successive terms, is given by what? What did you have for that? Brendan?
G of 1 times 1 minus r and n over 1 minus r.
Awesome. Raise your hand if you have the same thing as Brendan. Great. These are the tools, right, that we're going to build on today. We're going to make a connection between a partial sum, which is a series, and a finite series, and an infinite sum, right, which will lead to infinite series. So we just need these as our building blocks today. We're right where we need to be, and we've got a big day in store, so that's exciting. Let's take a look then at our partial sums. So we can calculate a partial sum of a sequence, depending upon how many of the terms you want to sum together. S sub 1 just refers to the sum of one term in the sequence. And so I simply go to my sequence, whose terms are given by t sub n, and sum up one term. Well, that would just be the first term here. And so 1 over 2 times 1 is 2 minus 1 is 1. So 1, are you getting 1 for the first term? So the sum of that one term is 1. S sub 2 would take the first term and the second term and sum them. So let's figure out our first term we have is 1. Our second term would be 2 over 2 times 2 is 4 minus 1 is 3, so 2/3. You guys get 2/3? So 1 plus 2/3. And we can see what that is. That would be what? 3/3 plus 2/3 is 5/3. You guys getting 5/3? Awesome. S sub 3 would be the sum of the first three terms in that sequence. So we've already got our 1. We've got our 2/3. Plus our third term would be 3 over, oh, you see the pattern now? 2 times 3 is 6 minus 1 is 5. So I'm getting 3/5 for my next one. Are you guys getting that? Awesome. And so that would be 15. Bless you. That would be 25/15 plus 3 is, so is that 28/15? Are you guys getting that? 28/15? Let me do it with the calculator. I'm bad with numbers.
At 34.
34/15? Oh, good. Good catch. Thank you. And we're still summing. And we've got 1 plus 2/3 plus 3/5 plus, and our fourth one now would be 4/7. And for your reduced fraction, what did you get for that, Tyler?
298 over 105.
298 over 105. Excellent. Raise your hand if you have the same list of partial sums. So S sub 4, you got all the 298 over 105. Great. Then we're going to combine these idea of a finite series, right, where we have a certain number of terms that we're summing together with an infinite series. And we had some good conversations in the groups last time as I was walking around finite versus infinite, as well as some pronunciation issues too, so that's great. All right, I'm going to go ahead and pause the recording. We'll take care of OCL number C. So what then is a finite series? So what is a finite series? Well, a finite series, right, is what you've already calculated. You've calculated those partial sums. A finite series is the sum of a finite number of terms in a sequence. Our S sub 4 from Bellwork was a finite series. It summed up 4 terms in a sequence. So summing a certain number of terms in a sequence is a finite series. That's a set number that we can calculate, right? That's a set number that we can calculate. If it's an arithmetic sequence or a geometric sequence, we have a formula that allows us to calculate that, and that was part of your Bellwork. But if we don't have a formula that we can use, we could still do it by brute force. Even if the number of terms are large, we could sit there and continue summing together terms until we got the value of the finite series. So this is defined, and we can get a certain number by summing up. Let's go ahead and compare the two main categories that we've looked at thus far. And so we've investigated arithmetic sequences, and we've investigated geometric sequences. So what's the pattern that connects successive terms in general for arithmetic? Well, in general, my pattern that connects terms in an arithmetic sequence is addition or adding, right? So let's kind of get this all in one place here. So adding versus geometric, what's kind of my pattern that separates successive terms? Danny?
Multiplication.
Yeah, we multiply between successive terms. What function family do arithmetic sequences most closely resemble? Right? What function family do they most closely resemble? Vivian? Linear. Thank you. So similar function family would be linear versus, and did you guys get that when we were discussing the, or when you guys were working the last activity? What function family do geometric sequences most closely resemble? Any?
Exponential.
Exponential. Good. Thank you. Here. Recursive formula for arithmetic. These are easy to spot, right? We've got our big brackets. For a recursive rule, we need two things: a start value and then a rule. A rule that gives us our current term based on the previous term. What is it that we do? So we need a start value. We need a sub 1, I'll call it some constant k. And then we can calculate the current term by taking the previous term, call it a sub n minus 1, and then doing what to it? Well, we'll add on that constant difference between successive terms. So like plus the versus a geometric sequence, its recursive definition, we still need some starting value, the first term. Well, again, I'll call that k. And to get the current term, call it g sub n. What are we going to do to the previous term? We're going to multiply it. We're going to multiply it by that constant ratio r, right? That constant multiplier between successive terms. So r times g sub n minus 1. Our explicit formula for arithmetic, bless you.
Bless you.
Our explicit formula for arithmetic, right, is a function rule. It'll give us the value of the nth term just by plugging in. Go ahead and share with the class the generic form for an explicit formula for arithmetic when I call you. What's my arithmetic explicit formula in general look like? Courtney?
A sub n equals a sub 1 plus d times n minus 1.
Absolutely, thank you. And you can see here, right, that I've got my constant rate of change multiplier there, and this n minus 1 input kind of subtracts off for that first term. That looks like a linear function. My geometric explicit formula, right, gives us the nth term in a geometric sequence by taking the first term g sub 1, multiplying it by my constant ratio r raised to the n minus 1. A finite series is just the sum of a certain number of terms in an arithmetic or geometric sequence. So for our purposes, right, a finite series would be the sum of the first n terms. In an arithmetic sequence, we did for Bellwork, right? That's just my n times a sub 1 plus a sub n, close, all over 2. Versus our geometric, the sum of n terms in a geometric sequence is given by g sub 1 times quantity 1 minus r to the n all over 1 minus r. Cool. So that's where we are, right? And let's see where we're going. So we've got our new summing notation, and that's going to help us build from finite series to infinite series. So every series has two sequences associated with it, right? The sequence of the terms which produce the series, so the sequence of the terms in this particular finite series would be the actual term values that I'm going to be summing together. And so if I were to make a list of those terms, if there were only 5 in this finite series, the first term, t sub 1, would be given by the value of t sub n, right? When n equals 1, that would be 1/2 to the first is 1/2. My first term is 1/2. Here I'm only going to 5. My second term, if I were to list out the terms in this sequence, would be 1/2 to the second would be 1/4, yes? 1/2 to the third would be my third term in the sequence, or 1/8. 1/16. And what would be our last term? Our last term in these 5, right? In these 5 terms, Riley?
32.
Great. So because we're only going, right, the first 5 terms, we can list those 5 terms. And this is the sequence of terms which will be used to produce the series. But a series isn't the term values. A series is the sum of those term values. And so while the first sequence associated with the series is the sequence of terms, the second sequence associated with every series is the sequence of partial sums leading to that ultimate sum sought. What? Well, if I were to start at 1, right? If I were to start at 1 and begin summing, I know that my first sum, my first partial sum, s sub 1, will be 1/2. So s sub 1 equals 1/2. My second partial sum would be the sum of the first 2 terms in my sequence. So that would be the 1/2 plus the 1/4. So my second partial sum, s sub 2, the sum of the first 2 terms would be 1/2 plus 1/4. And that equals 2/4, 3/4, 3/4. You guys getting 3/4? Not very nice. My third partial sum, s sub 3, the sum of the first 3 terms in my sequence, would be the 1/2 plus the 1/4 plus the 1/8. Go gadget on. So for us, that would be my 1/2 1/4 plus my 1/8. And we're at 6/8 plus another 8 is 7/8. That gives me 7/8. Yes? Awesome. My fourth partial sum, call it s sub 4, would be given by the sum of the first 4 terms. I'm almost there because there's just 5, so this would be 1/16. Are we starting to see the pattern here? This would be 14/16 plus 1 more is 15/16. Can I go right to it? And 1 more s sub 5. Any guesses as to what this might be without doing it? Grace? 31/30 seconds is correct. So the first sequence associated with a series, and I'll come back to this, the first sequence associated with every series is the sequence of actual term values. The second sequence associated with every series is the sequence of partial sums. I want you to go ahead and look at these partial sums. S sub 1 is 1/2, 3/4, 7/8, 15/16, 31/30 seconds. Right? Does it seem like these partial sums are converging to a particular value? Well, let's list those sequence of partial sums again. We had 1/2, then we had 3/4, then we had 7/8, then we had 15/16, and then we had 31, 30 seconds, you said, Grace? Can we generalize the formula for this, the nth partial sum in this particular series? Well, yeah. Can we write a formula based on n that would give us, right? That would give us the nth partial sum? Yeah. Well, what's the denominator, right? What's the denominator in my formula? How does that relate to my number nth for the sum? Well, my first denominator was 2. My second, when n equals 2, is 4. My third was 8. My fourth was 16. So what are we doing, right, to get our denominator? Tyler?
2 to the n.
Yeah, 2 to the n will be my denominator of the nth partial sum. What about the numerator? How's that connected? Who's got it? How would I get my numerator? Kobe?
2 to the n minus 1.
Yeah, it's 2 to the n and then just one less than that, right? So we could generalize the value of the nth partial sum by writing a formula. 2 to the n minus 1 is my numerator over 2 to the n is my denominator. Cool. I wonder how that's going to come in handy. So then, what is an infinite series? Right? What is an infinite series? And I heard you guys talking about this the other day. Well, if we are now extending our sum, right, beyond just a certain number of terms, but we continue summing to an infinite number of terms, that's the sum of an infinite number of terms in a sequence. We continue summing the terms of a sequence forever and ever and ever. At first, we might think that this sum would continue to grow and grow and grow since we're continually adding forever. However, it turns out that many of these series converge and equal a particular finite value. Even though we're dealing with an infinite sum, an infinite series, it equals a particular finite value, and we're going to see how that works. So we have the sum of not the first 5 terms like we just developed, but the sum of an infinite number of terms. What? Yeah. We started summing, there's our S sub 1, and then we kept on going. Right, there's our S sub 2, and we kept on going. Right? Could we determine the value of this? Well, we're continuing to add things, but what do you notice about the value of each term as n goes to infinity? And what's happening to the value of each term as n goes to infinity? T sub 5 was 1/32, right? What's happening to the value of each term if n gets larger and larger? Danny?
It's getting closer to 1.
The sum was, we had 31/32 was our last one, didn't we? And we could figure out what the next one was because we wrote a formula, right? The next one would be not 30, but 63/64. Would that be it? 63/64? Gosh, that is getting closer to 1. And so the limit of S sub n, as n goes to infinity, right, will give us the value of the infinite series, if there is one, right? If there is one. If the limit of the partial sums exists, then there's a finite sum and the series is said to converge. Danny thinks this bad boy converges, right, already, and we're going to see if we can show that algebraically. If the limit of the partial sums does not exist, right, that is, if the sum continues to grow, equals infinity, right, then the series diverges. And so if the limit of the partial sums does not exist, then the series diverges. All right, so a big question surrounding our discussion is going to be, will the sequence of terms ever converge? And if so, will the infinite series, that is the sum of the terms in said sequence, converge? Right? That's what we're going to investigate next. And so, if it's an arithmetic sequence, will the terms ever converge? Is there a particular value that the term values are approaching? If it's a geometric sequence, is there a particular value that the term values are approaching as n gets infinitely large? Then we can answer the question, well, does the infinite series, the sum of the terms in that sequence, converge? Is there a particular value that the partial sums are approaching, right? As n goes to infinity, and we're going to answer that question for both arithmetic and geometric, and that's our task, right? That's our goal. That's the driving question. All right, let's go ahead and look at this infinite series. You can spot an infinite series easily because my top index there is infinity, right? We're going to continue summing terms forever. If I were to just list the first few terms here, right? I know we'd start when n equals 1, evaluate my term value, right? Increment up my increment to 2, and then keep generating term values. I'd be summing them together. So here, my first term would be 1 plus 1 is 4. You guys see that? 4 plus increment my value n by 1. My second term would be 3 times 2 is 6 plus 1 is 7. Is that right? 7? Yes? Plus, because I'm summing, my third one would be 3 times 3, 9, 10. Oh, well, we see the pattern. What type of sequence is this? Right, what type of sequence is this? Vivian? Arithmetic sequence, right? And so we don't have to evaluate that term value for every value of n. We can just follow the pattern out. It looks like we're going up by 3 every time. So 4, 7, 10. Courtney?
13.
13. Right? Dot. All right. If you consider the sequence of partial sums then, right? The sequence of partial sums, S sub 1 would be 4, S sub 2 would be 11, S sub 3 would be 21, S sub 4 would be 34. Does it appear as though the limit of partial sums is going to exist? What happens to the value of the sum of these terms as we continue adding terms to it? Is this going to approach a particular value? No. It's going to be infinite, right? My term values continue to grow. Therefore, my sum will continue to grow. As n gets infinitely large, the sum will get infinitely large. So the limit is n goes to infinity. My partial sums is infinite. That does not exist. Therefore, the series diverges. The series diverges. Let me get in there. So much better. In fact, we could argue that for all arithmetic, right? Will my arithmetic terms ever approach a particular value? Well, they'll continue to increase and decrease in an increment of d, a constant difference every single time. And so my term values will not converge to a particular value. Therefore, my sum is guaranteed to not converge to a particular value, and all arithmetic sequences will diverge. Emily?
Oh, I was just going to ask, like, don't we usually use does not exist with, like, 1 over 0?
Okay. Yes. What would, right? What would our general form for 1, a constant, over 0, or a quantity approaching 0 be? Would that be indeterminate? Right? Or would that be infinite? Right? The difference between 1 over 0 versus 0 over 0. If I have constant over 0, when I'm trying to evaluate a limit, is that indeterminate? No. Is that infinite? Yes. Right? That's what we got when we tried to evaluate a limit expression. If my denominator was shrinking towards 0, but my numerator was constant, that's when we got our vertical asymptotes. Right? That's when we got our vertical asymptotes. So that's infinite. Because this is not a particular value, the limit does not exist, right? We say that it equals infinity to describe exactly the manner in which it does not exist, but if it's not a particular value like 7/3 or negative 1/7, right, or 26, then the limit does not exist. If the limit does not exist or is infinite, the series diverges. Good question. Other questions about that? I feel like we're going to have one of our boxes then. But hang on, let's keep going. What category function is this? All right, what is my term? My term in each sequence is given by what kind of sequence? Right? Geometric, right? I've got a base 2 raised to the nth power. If I were to start listing out this infinite series, I can begin with term 1, 2 to the n, plus 2 squared, plus 2 cubed is 8, which is my third term, plus 2 to the fourth is 16, plus forever and ever and ever. Do my term values, right? Do my term values, 2, 4, 8, 16, are they approaching a particular value? Are they converging? No, they're continuing to balloon towards infinity forever. Therefore, will my sum, the infinite series, right, converge? No, it'll be guaranteed to continue to grow and grow as I sum larger and larger terms together. This is, again, will be infinite. It does not exist. If the limit of partial sums does not exist, then the series is said to diverge. Well, it feels like we're not really getting anywhere. We looked at an arithmetic series, right? Or I'm sorry, an arithmetic sequence, and then the sum of an arithmetic sequence, and we got diverges for that series. We looked at the sum of a geometric sequence, and we got diverges for that series. Let's consider another one. So here I have an infinite series. This time, well, isn't this still geometric? So is this going to diverge? Well, I don't know. Let's start listing our terms. So first term would be 1/3 plus, because I'm summing. My next one would be 1/9. Yes? Plus, my next one would be 1/27, 1/81. Yes? As I continue to consider larger and larger term values in the sequence, does it appear as though the term values are converging? Yeah, what do the term values seem to be approaching as n gets infinitely large? Brendan? 0. If my term values are approaching 0, then it just might be plausible, right, that the sum itself might converge. That is to say, if the quantity that I'm adding, right, to my partial sum to get the next partial sum is approaching 0, then my overall sum, right, could be leveling off, could be approaching a particular value, in which case the limit of the partial sums as n approaches infinity would equal a number. It would exist, and I would have a series that converges, and that's what we care about, right? That's what we're after here. And so let's see if we can't fill in some of our chart. For an arithmetic sequence, will the sequence of terms ever converge? As I continue adding a particular difference, d sum or difference, to successive terms? No, they'll continue to grow or shrink by that set addition or subtraction. And so, no, never. If the term values do not converge, then their sum will never converge. Hey, we got half of our chart. That's pretty sweet. Will the sequence of terms ever converge? For geometric, well, we just saw two geometric series. In the first case, we considered the geometric sequence given by g sub n is 2 to the n, right? G sub n is 2 to the n. Did the term values here converge? No. In the second geometric sequence, 1/3 to the n, did the sequence of term values converge? Yes. So what was qualitatively different between these two geometric sequences? Right, what was the difference between these geometric sequences? Rylan?
One of their ratios was larger than one, and the other was smaller than one.
Okay, so when we had the larger than one, the term values ballooned, thus the series diverged. When the ratio r, 1/3, was less than 1, the term values shrunk, they converged to 0, and then we're guessing that this this infinite series might just exist. Well, the term values, for sure, we can fill in this chart. So yes, Riley, you're absolutely right. So if R, right, or the magnitude of R, I should say, bless you, is greater than 1, then no. So if my constant multiplier R, if the magnitude of R is greater than 1, then no. However, we just saw that if the magnitude of R was less than 1, then yes. What about if R equals 1? What if R equals 1? Well, I don't think we have to make a new slide. Let's just pretend R equaled 1. We'd have 1 plus 1 in the second is 1 plus 1 plus 1. Did the sequence of terms converge? Is there a particular value that the term values are approaching as n gets infinitely large? The term values are converging, right? Don't they equal 1? Isn't that a particular value that the term values are approaching as n gets infinitely large? It's constant. It's always 1. You're thinking, no, for the series, if we sum those terms together, 1 plus 1 is bigger, then 1 plus 1 is bigger, is bigger, is bigger. That will continue to balloon. And so this would be a yes here, but this will be a no here. This will be a no here. And by gosh, I'm just wondering. Here's what we're after. Danny thought that when my base was 1/2, right, and we considered the sequence of partial sums, 1/2, 3/4, 7/8, 15, 16, 31, 32nd, 63, 64th, boy, it looked like the limit of those partial sums was existing, and they were getting closer and closer to 1. If we consider the limit of partial sums for the infinite series that sums the geometric sequence terms 1/3 to the n, right? We're thinking that this might be approaching something as well. So could we consider, right? Could we consider the limit as n goes to infinity of a geometric series and see if there's a particular value that's being approached? Yeah, I want one more slide here. And so when we had when we had 1/2 to the n, right? And we considered our partial sums. And we had our S sub 1, and we had our S sub 2, and we had our S sub 3. We had our S sub 4. Can we generalize that formula? Yeah. Our denominator was 2 to the n, and our numerator was 2 to the n minus 1. If the series, the infinite series, is equal to the limit as n goes to infinity of the partial sums, and I have a, gosh darn it, formula for my partial sums S sub n, could I try evaluating the limit of my partial sums as n goes to infinity? You bet your boots. Let's consider the limit as n goes to infinity of S of n. In this case, that's the limit as n goes to infinity of 2 to the n minus 1 all over 2 to the n. How can I evaluate this? Well, as n goes to infinity, the numerator goes to infinity. As n goes to infinity, the denominator goes to infinity. And so I'm having a hard time evaluating this algebraically. Unless, gosh, can we break up that fraction, that sum or difference, right, of terms in the numerator? It could be rewritten as a sum or difference of individual fractions each with the same denominator. Keep your limit expression, please. Isn't this the limit as n approaches infinity of 2 to the n over 2 to the n? Minus 1 over 2 to the n? Which in turn is given by the limit as n goes to infinity of 1 minus 1 over 2 to the n. Can we evaluate this limit? Well, certainly. I know the limit of a constant is the constant itself. Danny? Oh my gosh. I think we're closer. What's going to happen to this denominator, 2 to the n, as n goes to infinity? Well, we saw that before as we were considering term values in my geometric sequence 2 to the n. 2, 4, 8, 16. 2 to the 1,000. 2 to the 1 million. What happens to 2 to the n as n goes to infinity? Goes to infinity, 1 over infinity. This quantity is going to go towards what? 0. Which means the value of my limit as n approaches infinity of 1 equals 1. Gosh darn it. Danny, you win the prize. Now, we just did a single case, but we could go through and we could do the same thing for the 1/3. In fact, I urge you to consider trying to generalize the formula for the nth partial sum, S sub n, of the 1/3, right? The 1/3 to the n. Maybe we'll see that again sometime. All right, so recall the formula for the partial sum of the geometric sequence. Let's see if we can't generalize this. This was your Bellwork. If we summed up n terms, right, in a geometric sequence, if we sum up n terms, we know that the sum would be g sub 1 times quantity 1 minus r to the n all over 1 minus r. Now consider the limit as n goes to infinity of S sub n, right? What's going to happen here as n goes to infinity of g sub 1 times 1 minus r to the n all over 1 minus r. If the limit of this partial sum exists, then there is a finite sum. It equals a number like 1, right? And the series converges. So can we evaluate that? I hope so. So here we go. We've got our limit as n goes to infinity of g sub 1 times quantity 1 minus r all to the n over quantity 1 minus r. We know the limit of a constant is the constant, right? And so if we were to apply our limit laws and break this up into products and sums and differences, what's going to hinge on is this value of r. As I repeatedly multiply that ratio r by itself as n goes to infinity, right, we've got our two separate cases here. We've got if r is greater than 1, right, if r is greater than 1, then this quantity is going to balloon and I will end up getting an infinite expression over a constant, and that does not exist. And so the series will diverge and we say the series diverges. Here's the kicker. If the magnitude of r is less than 1, however, then the limit as n goes to infinity of g sub 1 times 1 minus r to the n all over 1 minus r. What happens to r to the n if r is less than 1? Like 1/2. 1/2 to the 10th, 1/2 to the 100th, 1/2 to the 1000th. Well, that repeated multiplication makes this term go towards 0, which leaves me with the limit as n goes to infinity of g sub 1 times 1 is just 1 all over 1 minus r, and I've generated a formula for the infinite series of a geometric sequence when r is less than 1. This is a big deal. So we've determined that a geometric series converges, and I can tell just by looking at my term rule, t sub n, if r is less than 1, then I know that the series will converge. The infinite series will converge. That's pretty sweet. Sorry, we need to say equals one more time. That's a constant in n's eyes. So we get g sub 1 over 1 minus r. This is a big deal. All right, so what are we considering now when we ask the all-important question, bless you, does the series converge or diverge? So we're thinking with our little think bubble, is the sequence of terms converging enough to ensure that the sum will also converge? Remember, I'm summing together an infinite number of terms. I need those term values to be shrinking towards 0 quickly enough so that the sum of those terms is also leveling off, right? It's not, the sum of the terms is not going to equal 0, it's going to level off towards something, right, in general. So we've got our explicit formula for arithmetic. My explicit formula, a sub n, is given by Courtney told us a sub 1 plus d times quantity n minus 1. For geometric, g sub 1 is given by, g sub n is given by g sub 1 times my constant multiplier r to the n minus 1. For a finite series, the sum of n terms is given by n times quantity a sub 1 plus a sub n all over 2. For a partial sum, a finite geometric series, I know S sub n is given by g sub 1 times quantity 1 minus r to the n close quantity all over 1 minus r. For an infinite series, an arithmetic series always diverges. For a geometric series, if, and we can now add or equal to, if r is greater than or equal to, the magnitude of r, I should say, is greater than or equal to 1, diverges. However, if magnitude of r is less than 1, then it converges to, I'll use the infinite sum is given by g sub 1 over 1 minus r. That's super sweet. Good talk. Good talk. All right. So we're thinking, do the term values converge to 0? If the term values don't converge to 0, right, then there's no hope for my infinite sum, right? My infinite sum, the infinite series, to exist. It will always diverge if my term values don't converge to 0. So I need the limit of the term values to be 0 if there's going to be any hope of convergence. Just because the terms shrink in value towards 0 doesn't guarantee the infinite series will exist. They need to be shrinking towards 0 quickly enough such that the partial sums converges to a particular value, and then the infinite series will exist. So the infinite series will denote by, right, s sub infinity there. There's an infinite series. That's the limit of the partial sums as n goes to infinity. And we already saw how that was the limit as n goes to infinity. And wasn't that, for this particular one, that was 2 to the n minus 1 over 2 to the n, right? And we did a bunch of work here. And what did we get, Danny?
G sub 1
Well, I mean, when we did that, we ended up getting 1, right?
Oh, yeah.
Yeah, I'm just saying. And so we're doing our abbreviated abbreviated, what are you guys gonna do when you're asked the all-important question, does the infinite series, right, converge or diverge? You're gonna first think, do the term values approach zero? If they don't approach zero, then automatically this infinite series will diverge. Does not exist. However, if the term values approach zero, I then need to consider the limit of the partial sums, and then goes to infinity. If that value exists, if that limit exists, then I know the infinite series exists, and I can calculate its finite sum. All right, so we did that, and I had space for us to do that again, and we got 1. So let's go ahead and do some practicing now. Tell whether the sequence of terms is arithmetic, geometric, or neither. We're going to do 4 together, right? We're going to do 4 together. Then we're going to have closure. Then you guys are going to have a chance to practice. I want to do the 4 together because they're similar to the last part of your infinite series practice. That way you guys will know what's up. Okay, so what's our thought process? Our first thought process is, do the term values, right, converge to 0 as n goes to infinity? Well, as I consider the first one in letter A, will my term values approach 0? No, clearly not. This is a geometric sequence with r greater than 1. R equals 4 here. And so this is guaranteed to diverge without any work. My number 1, I can first say the sequence is geometric. This is the geometric sequence. With constant ratio r equals 4, which is greater than 1. Therefore, the series will diverge. Hey, 1 down. On 4, that was a quick practice. Next. Arithmetic, geometric, neither. Quietly tell your partner to be ready to share with all class. Arithmetic, arithmetic, geometric, neither. Tyler and Emily, what do you guys think? Arithmetic. Will the terms converge as n goes to infinity? Nope. They'll continue to increase or decrease, in this case increase by 1/4. So this is an arithmetic sequence. Do any arithmetic series converge? No. Arithmetic, so automatically diverges. 2 for 2. Designing. Arithmetic, geometric, neither. Sydney, Kobe. Geometric. Ding, 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 ding. We got geometric. With, what's my R value here? Or what's my R value here? Grace? 1/4. Is 1/4 greater than or less than 1? Well, that's less than 1. So what do we know about geometric series? With R values less than 1, will converge. In fact, this converges to the infinite sum g sub 1 over 1 minus r. And we can calculate that. What's g sub 1? Well, that would be 1/4 to the 1 is 1/4 times 2 out front is 1/2. You're getting 1/2 for your first term. Over 1 minus my R value was 1/4. Doesn't look too bad. I get 1/2 over 1 minus 1/4 is 3/4. Ah, the F word. More F words. F word, F word, F word. 3 and 1 thing. Gosh darn it. No problem. I know I can divide by a fraction by multiplying by the reciprocal. So this equals 2, 3, 4, 2/3. 2/3? Yeah. Yes, I like math. But that's still pretty neat that I can continue summing an infinite number of terms forever and ever and ever, and yet have that sum equal some finite value like 2/3. Still adding. Oh yeah, I'm still adding right now. But that sum is still going to converge to the value 2/3. That's pretty sweet. One to go. Arithmetic, geometric, neither. I don't know. I'm going to start listing the terms and summing them together and see if this resembles an arithmetic or geometric sequence. Here we go. Term 1. 1 over 2 minus 1 is 1 over 1, 1. Plus. Next term. 2 over 3. Plus next term. 3 over 2. 3, 6. 3/5 plus 4/7 plus 5/9. You guys see it? Yes? Awesome. Do the term values converge? Do the term values converge? Well, it appears as though they're shrinking, right? 2/3 is less than 1, and 3/5, 0.6, is less than 0.66 repeating, and 4/7 is less than 3/5. Let's see what happens as n gets infinitely large. So if I had n over, guys, go ahead. We're going to do a command really quick. This is pretty cool. So if I entered, right, my term rule in the y equals menu, and I go to my table, and because I was with my advanced algebra buddies, I had auto for the table, but we all know that ask is where it's at for the independent variable. And I went to my table, and I let n get large, like 10, 100, 1,000, 100,000. Do the term values converge? Yes, they do. They converge, and what value do they converge to? 1/2. Let's see. So the term values converge. Does the series converge? No, I know. The term values converge. What do the term values converge to? Which means that as n gets infinitely large, what am I continually adding to my sum? 1/2. Forever. 1/2. 1/2. 1/2. So gosh, it's going to behave a lot like an arithmetic. It's not arithmetic, right? There's not a constant difference in success that connects every successive pair of terms. And yet it will behave much like one at the very end because I'm going to continue to add 1/2, 1/2, 1/2, guaranteeing that the series diverges. So first of all, we have to say neither to respond to the prompt. However, the term values don't converge to 0. This doesn't equal 0, so there's no hope. And even if it did equal 0, it doesn't mean that it automatically converges. It has to be converging to 0 quickly enough. And there we get, right, reminding us about rates of change in calculus, and this sets the stage now for our series unit after winter break. Okay, so series diverges because the term values did not converge to 0. Automatically will diverge. All right. So let's go ahead and close it up then. These answers might seem similar to you, right? And that's because they're decidedly connected. So it's okay if some of your responses seem similar. These are the big ideas, though, from today's discussion. A written response from each partner pair, and then we'll share. How is it even possible for an infinite sum to converge? For a series to converge, the nth term of the sequence must do something. It has to do something specific. What must be true about the partial sums of a series in order for the series to converge? And what must be true for a geometric series to converge? So go ahead and share with the class then, how is it even possible for an infinite sum to converge? How is it even possible? All right, Riley?
If you keep adding numbers that get closer and closer to zero, it's going to approach.
Yeah, it could. So if we're adding terms that are approaching zero, so if we're adding together terms that are approaching zero in value, then it's possible the sum will level off to a particular number. And I'm going to go ahead and just put quotation marks here, level off, right? If we're continually adding, but we're adding terms that are getting closer and closer to zero in value, then it's possible that the sum could level off to a particular number. That's my super technical math term for BC. To have a hope of a series converging, what must the nth term of the sequence do? Right? What does it have to do then? What does that nth term have to do? Sophia? Yeah, it has to approach zero. Right, it has to approach zero to have any hope for the series. If the limit as n goes to infinity of t sub n, right, the nth term does not equal zero, then automatically the series converges. Bless you.
Bless you.
What must be true about the partial sums of a series in order for the series to converge? What has to be true about the partial sums? Vivian?
They have to approach a constant.
They have to approach a constant, so the limit of the partial sums has to exist. It has to approach some constant. So this limit must exist. If I can evaluate the limit as n goes to infinity of the partial sums formula, and it equals some number, if it exists, the limit must exist, then the series converges and equals the value of that limit L. So this limit must exist in order for the series to converge. In a specific case for geometric, what must be true for a geometric series to converge? Kobe?
R has to
Yeah, the magnitude of R has to be less than 1. Raise your hand if you had number 4. The magnitude of R has to be less than 1. Awesome work, you guys. This is not included in your printout, and so I want you to go ahead and jot it down if you need to, because I filled up that last page. You're going to finish the Infinite Series practice. That's what you're going to work on right now. There's 3 stamps. The stamps are 1F, 2E, 3B. Then the sequences and series worksheet is OTL number 1. And so the sequences and series worksheet is OTL number 1. And I'll label the next one as OTL number 2. I'm going to go ahead and stop the recording now and upload it to our